All right, guys, so in our previous lesson, we talked about how can we find areas of shapes that have, squares or rectangles, triangles, or circles. But today, we're going to start to get into the question that how can we find some area that's under a shape that's not something that we just have an easy area formula with. And what we're going to do today is find a way to estimate this area. Okay, so say this is some function f of x. I'm trying to find this area from 0 to 8. I don't give you an equation for this. I just give you a crappy picture that I made in Microsoft Paint. Okay, so what I'm saying here, we can estimate this area by drawing rectangles under it. So if it's not rectangles, let's make it rectangles. So there are three different ways I can do this. First off, I'm going to split it into two intervals. So instead of going from 0 to 8, I'm going to split it into one interval from 0 to 4 and also an interval from 4 to 8. So we're going to go, okay, here's 0 to 4, here's 4 to 8. So there are a couple different ways I can do this, and I can basically do what's called using the left endpoints, the midpoints, or the right endpoints. So for the left endpoints, what I'm basically doing is I'm using the height on the left side of each interval. So I'm going to make two rectangles. So for my integral from 0 to 4, I'm going to go up to the height of the function on the left side at 0. So it has that height there of f of 0. And I'm going to go over to 4 and draw a rectangle there. And then I'm going to, for my next one, use the height at 4 and then go over and use that. Okay, so again, I've split it into two parts, and in each part, I'm using the height, the value of f, at each one. So I'm going to do base times height, because these are both rectangles, right? We know the area of a rectangle is base times height. So now I want to find this left area. It looks like 1, 2, 3, 4, 5, 6. It has a height of 8. It has a base of 4. So I'm going to do 4 times f of 0 here, the height at 0, which is just 4 times 8 plus. And then on my next interval that goes from 4 to 8, I still have a base of 4, but I use the height at 8, which in this case, the height at, the height at 4, because my left endpoint is 4, right? So I'm saying, all right, I'm going from 0 to 4, I'm going from 4 to 8, so I'm using the height at 0, and I'm using the height at 4. So this turns out to be, of course, 4 times, looks like about 3/2, so that's 32 plus 6, which is 38. Okay, now you might say, well, lefties are weird, so why don't we just use the height at the right endpoint? So that's a right endpoint sum. So we use the height on the right side of each interval. Okay, so again, we're going from 0 to 4, we're going from 4 to 8, but now we're using the height on the right side of each of these. Okay, so here is 4, and then of course here's 8. So when I make my rectangle now from 0 to 4, I'm using the height at 4 and going over. I'm using the height at 8, which is 0, and going over. So I'm saying, okay, first off is 4 times the height at 4 for the first interval, and the next interval has a base of 4, and I use the height at 8, so 4 times f of 8. So in this case, that would be 4 times 3/2 plus 4 times 0, which is 6. Okay, and again, what I've done is I've just kind of found that rectangle, and in the other example, I found like the area of both of these rectangles and added those together. Now, you might notice that both of these are incredibly crappy estimates. So you might be saying, hey, instead of using the right or the left, why don't we use the middle? Why don't we use the height at the midpoint? So use the height in the middle of each interval. And that's the midpoint strategy. So if I go from 0 to 4 and 4 to 8, what if I use the height at 2? So I still have a base of 4, but I use the height at 2, because that's in the middle, and then halfway between 4 and 8, of course, is 6. So what if I use the height at 6? So if I'm splitting that up there at 4, so I'm saying, okay, what if I use the height at 2, go up to there, and use that? Oh, geez. And what if I use that for the height of the whole thing? As I go from 4 to 8, what if I'm going to actually draw a good picture here. So what if I go from 4 to 8, I use the height at 6, and then I go over like that. Okay. Now, obviously, this still isn't perfect, but hopefully you can see this is going to be a little better estimate. So when I use the height at 2, it looks like that's a 4. When I use the height at 6, it's hard to say. Maybe that's like 3/4, 2/3, maybe. Let's go 3/4. So 4 times 3/4. So that gives me 19. Now, again, none of these are perfect, but these are just 3 different ways that you can estimate the area by finding it as rectangles. Okay, and what we're doing here, this strategy, these are called Riemann sums. And Riemann is a dude, one of the most famous mathematicians of all time. The way to pronounce his name is Riemann. If you pronounce his name Riemann, I will kick you out of class. Riemann. And basically what we're doing is we're summing together a bunch of things that are in the form f of x times some delta x, where that delta x, that change in x, that's the width of the base. And I'm just adding a bunch of those together to get an approximation. All right, now the next thing I wanted to do is what if you have 4 rectangles? So instead of splitting this into 2 rectangles, what if we split it into 4 intervals at 2, at 4, at 6, and at 8? Okay, cool. So again, we want to think about these. I always like to write down the integrals. So I say, okay, I'm going from 0 to 2, I'm going from 2 to 4, I'm going 4 to 6, and I'm going from 6 to 8. So each of these, of course, have a base of 2. So now I'm using the height. This problem is asking me to use the height at the left endpoints. So use height at 0 and go over, but only go over 2. Use height at 2 and only go over 2. Use height at 4 and go over 2. Use height at 6 and go over 2. So that's what you're doing. Now we can see it's still not perfect, going to be an overestimate for sure, but this hopefully will give us a better picture than the more crude picture we saw up here with 2 rectangles. So in each of these intervals, I'm doing like a base times height times plus base times height plus base times height plus base times height. So I'm doing a 2 times, okay, and I like to do this also. I like to circle the left endpoints so I remember which height I'm using. So I'm doing like 2 times f of 0 plus 2 times f of 2 plus 2 times f of 4 plus 2 times f of 6. Okay, so if I just take those values, that's 2 times 8 plus 2 times 4 plus 2 times, and then the height at 4 it looked like was, what, 3/2? Yeah, somewhere around there. And then the height at 6 was like roughly half. I think I said something different above, but who cares? Okay, so that's like 16 and 8, 24 plus 3 plus 1. Oh my gosh, math is hard. Looks like about 28. Now, still not a perfect estimate, but this is a better way to estimate. And as you would almost certainly guess, more rectangles is going to lead to better estimates. So that's something I would encourage. Okay, now, as you might also expect, as you go to infinity, the estimate becomes perfect. It's no longer an estimate. So what I mean by that is, and we're not getting into the nitty gritty, but if you take a limit as n goes to infinity of a Riemann sum using n intervals, if you take that limit as n goes to infinity, that is equal to the integral from a to b of f of x dx. So basically what it's saying is, if you take not just 10, not just 20 or 30 intervals, but if you break it down into an infinite number of intervals, you're no longer estimating the area, it actually finds the area perfectly. These are all estimates we've done today, but it's actually perfect if we were to take an infinite limit somehow. So what a dx, when you see that dx in the integral, what it means is it is an infinitely small change in x. So you'll notice this idea, this in the sum from f of x dx, when you take an infinite number of these sums, it turns into an integral with this infinitely small width. So that's not super important, but anyway, we'll talk about a couple other things. So one of the questions that the AP people like to ask is a Riemann sum an over or underestimate for a decreasing function? Okay, and the key that I want to let you guys know is draw a picture. This is not something I memorize. So in my head, I just say, okay, let's say I have a decreasing function. If I do a left Riemann sum, I use the height of the left side and go over. I use the height of the left side and go over. Hope you can see that just using this crude picture, we can see that it's going to be an overestimate. So in this case, the sum overestimates the actual area. And of course, the opposite of this is true if you use a right sum. So if you have a decreasing function, if you use a right sum, so use the height of the right endpoint and go over. Use the height of the right endpoint and go over. You can see that that right sum underestimates the actual area, right? There's some area that it just doesn't get to, it doesn't find. So, and obviously if you have an increasing function, the opposite is true, but you can draw pictures to kind of figure that out. Okay, so that's how that goes. Let's do a couple more problems here. What if they give you an equation, right? So if I ask you to estimate the area under the curve 1 plus x squared from 0 to 4. So what that's saying is if you had this parabola of 1 plus x squared and you wanted to find the area from 0 to 4. and you didn't have a graph, you just had this equation, how could you do that? Well, the first thing I would do is if you're using two rectangles, I'd write down the intervals. So if I'm going from 0 to 4, I'm going from 0 to 2, and then also from 2 to 4. So if I ask for a right Riemann sum would use the height at the right endpoints, right? So that'd be like base times height, and both these, of course, have a base of 2. So I'd use the base times the height of the left interval there, and then the second one, base times the height, not the left interval, yeah, that's the left interval, the right side of the left interval, and then 2 times the height at the right side here. So I'm using the right endpoints of each one. So we could just get these out of here, right? If I needed to find f of 2, that's 1 plus 2 squared, that's 5. If I needed to find f of 4, is 1 plus 4 squared is 17. So that's just 2 times 5 plus 2 times 17, which in this case is 44. If we want to use a midpoint Riemann sum, again, we do a similar strategy, right? If we go 0 to 2 and then 2 to 4, my midpoints there are x equals 1 and then x equals 3. I still have a base of 2 in each of these. So I would just do 2 times f of 1 plus 2 times f of 3. Now, the most common way you'll see, and then you plug this in or whatever, the most common way you'll see a Riemann sum on the AP test is with a table of data. So they'll give you a table and ask you to estimate this integral, this area, using a left Riemann sum. Okay, now again, I'm going to write the integrals out. So I have 0 to 3, I have 3 to 5, I have 5 to 6, and I have 6 to 10. So if I'm doing a left Riemann sum, I'm using the height at each of these. Now, one thing worth noticing, right, these bases change. This has a base of 3, this has a base of 2, this has a base of 1, this has a base of 4. So keep that in mind right out the intervals, and that you'll see the integral intervals are just the areas between these points. Now, if you just have a table, right, you can't find the actual value. There's no function you can plug in or graph you can look at. You literally just can only do a Riemann sum to estimate that. So if I'm going from 0 to 3, that's like 3 times f of 0. 3 to 5, we have a base of 2, so it's 2 times f of 3. 5 to 6, we have a base of 1, so 1 times f of 5. And then here we have 4 times the height at 6. And then for these, I'm just going to get these values from the table, right? They tell us the values of each of these f of x. So that's 3 times 5. And then that's 2 times 7. That's 1 times 3. And then that's 4 times 2. So that's like 15 and 14, so 15 plus 14 plus 11, geez, I think it's 40. Okay. So that's a left Riemann sum. We couldn't do a midpoint here because we don't have the values between, but we could do a right Riemann sum, right? We could just look at what are the right parts of each interval. So again, we just do 3 times f of 3 plus 2 times f of 2 plus 1 times f of 6. Oh, sorry, that shouldn't be 2. That should be a 5. My handwriting's bad. 2 times f of 5 plus f of 6 plus 4 times f of 10, and then just plug those values in. This is an important skill. Make sure that you can take the Riemann sum using a table. That'll show up on the AP test for sure. All right, we have one more thing to talk about. I'll do that in another video. Thanks for watching. Bring me questions to class, guys.